Today we're going to do a lower-tailed test for population proportion. Again, we're going to go to my teaching website. We're going to download case 8 in chapter 9, which is right here. In this problem, we want to test whether a proportion is at least 70%. Why? Because here in the setup of the problem, we have the news recently reported that at least 70% of economists, so at least is a keyword. I'm going to make that bold. 70%, I'm going to make that blue and bold. "70% of economists believe the stock market will go higher." So I'm going to put believe the stock market will go higher. And that's going to be red and bold. Okay, so that right there is pointing to our null hypothesis. Because what does at least mean? At least means greater than or equal to. And we need the proportion. We need the proportion of economists who believe the stock market will go higher. So this is our variable. An economist either believes this statement or doesn't. And our response variable is over here. So you want to test this news report, and you decide to survey 103 economists, and from various different universities. So these are the results from a survey, and there is 103 of them. 103 economists were surveyed in this particular survey, and some of them said yes, and some of them said no. It kind of looks like most of them, well, I don't know, kind of hard to tell from here. It looks like maybe it's split, yes, no. But we'll look at it in more depth a little bit later. So the data are shown in column A. A response yes indicates the economist thinks the stock market will go higher. So again, our variable is economist. An economist believes the stock market will go higher. And we want to know if at least 70% of economists believe that the stock market will go higher. So the first thing to do is to write our null hypothesis here and our alternative hypothesis. The null hypothesis states that the population proportion of economists who believe the stock market will go higher is at least 70%. That means the alternative hypothesis is the proportion of economists who believe the stock market will go higher is less than 70%. Now, an equivalent way to say the null and alternative hypothesis is here. In the null hypothesis, we have the difference in the proportion and the hypothesized value 0.7. We have that difference being greater than or equal to 0. We won't know the true population proportion, but we can estimate it with p bar. So p bar, or the sample proportion, is the point estimator for p, and the difference between p bar and 0.7 is the point estimate of that difference that is highlighted. Now, the question we want to know, the real question we want to know is the difference, is the point estimate of that difference negative and significant? That's what we're looking for. We're going to have a difference. The probability that the proportion, sample proportion, is equal to 0.7, whether that difference equals 0 or not, that probability is pretty close to 0. So we're going to have a difference. And the question we want to know is according to the alternative hypothesis, is whether that difference is significant and negative. Our hypothesized value is 0.7. Now, from the PowerPoint that we looked at the other day, we have the z-stat for a one proportion test. The numerator is the point estimator of the difference in either of the hypotheses. That's the point estimator of the difference. And in our example, the p0, the hypothesized proportion, is 0.7. So we need to compute the p-bar. We need to compute the sigma squared. And down here at the bottom, you notice that sigma squared is the hypothesized value, or 0.7, times 1 minus that hypothesized value, 0.7. So we're going to have 0.7 times 0.3. And the z-stat is approximately normally distributed if the number of economists in our sample of 103 believe that the stock market's going higher. Over here we have the number of economists in the sample who believe the stock market's getting lower. So both of those have to be at least 5, and they are. So I'm going to copy this and paste it into my spreadsheet, which is right here. Okay, so what do we need? We need the sigma squared, we need the p-bar, we need the hypothesized value, which is 0.7. So the sigma squared is 0.21. And how did I get that? I took 0.7, which is J8 here, and I multiplied it by 1 minus 0.7. So the sigma squared for this problem is 0.21. The p-bar is the count in this column here that goes from A2 down to A4. So we're counting the blue box here. We're counting the blue box when we report the economist said yes, the economy or the stock market will go higher. And then we're dividing that by the sample size. And the sample size is 103. And the way we did the sample size, we just counted. We used equal count A and then highlighted the blue box. And we got a count of 103. Now notice the p-bar is changing every time I hit the button F9 on my keyboard. And the reason why that's going on is because every time I hit F9, I'm sampling 103 different economists. Every time I hit the F9, I get the responses of 103 different economists. And so all of us in this class should have a different p-bar. The sigma squared doesn't change from sample to sample because we use the hypothesized proportion to compute sigma squared in chapter 9. So the only thing that's changing here is the p-bar. Every time I randomly sample 103 new economists, I get a different p-bar. So we have the sigma squared, we have the p-bar, we have the n. Now we need the point estimate of the difference between, we have the point estimator of this. Oh, sorry, I need to freeze this column. I'm going to copy and paste special this column. Now when I hit F9, I'm holding my responses of these 103 economists constant. So I'm looking at a given sample of 103. So now my numbers are stable. They don't change. The p-bar here, 0.718447, is the point estimator of that p. But what I'm interested in is this difference. I need a point estimator of that difference. And the point estimate of that difference is the p-bar minus the hypothesized value, 0.7. And that right there, this value here, is the numerator of my test statistic. So the next thing I need is the denominator of the test statistic, which is the standard error. The standard error is found by taking the square root, typing equal, square root SQRT, parentheses, E12, which happens to be the value for the sigma squared or population variance, divided by the n, which is 103 in this case. And so the denominator of my test statistic, known as z-stat, is 0.045153. So the last thing to do is, in this part of the question, is calculate z-stat. And it's just the ratio of the point estimate of the difference divided by, which is the numerator of the z-stat, divided by the denominator, which is the standard error. And z-stat here is positive 0.408531. Now in part C, we're given a significance level of 0.1. We need to conclude using this. We need a test conclusion. We need a conclusion for our test using a significance level of 10%. So our significance level is 0.1. And recall that we have a one-tailed test, so we divide the alpha by 1. Now why do we divide alpha by 1? Well, the alpha is divided by 1 because the alternative hypothesis tells us we have a lower tailed test. So I explicitly divide alpha by 1 to remind me that we have a one-tailed test. And remember, in previous discussions, we can find the critical value of this test in either the standard normal table, which I like to call the Z table, or we can find it in the infinity row of the T table. And if you find it in the standard normal table, you only get 2 decimal accuracy. So I like to find it in the infinity row of the T table. So we want to go to row infinity of the T table and column 0.1. We want to go to column 0.1 and the infinity row of the T table to get the Z critical value. So let's go ahead and open up the table of distributions that we use a lot in statistics. So first we have what I call the Z table, which is better known as the standard normal distribution. And I want to blow this up just a little bit. So we got to find 0.1, right? And I think we did this last class. The number closest to 0.1 is 0.1003. And it's in row negative 1.2 and column 08. So candidate number 1 for critical value, Z critical value, is negative 1.282 or 1.28. Negative 1.28. Well, we can find it to 3 decimals in the Z table. So we go to the T table, the T table. So we go to column 0.1 and notice what happens as the degrees of freedom rise. When the degrees of freedom are rising, that's because the sample size is increasing. So as we increase our sample size, the degrees of freedom rise, and the T critical values get closer and closer and closer to what we found in the Z table, 1.28. But the good thing about the T table is that we have 3-digit decimal accuracy. So in the infinity row of the T table, we find Z values. And because our tail is got an area of 0.1, we conclude that our critical value of this test to 3 decimal places is not 1.28, which the standard normal table told us, but 1.282. Now, I'm going to make this negative. Why do I make it negative? Again, we got to go back to the alternative hypothesis. The alternative hypothesis says what? It tells us what kind of test we have. Well, the proportion being less than 0.7 is pointing to the lower tail. And we have a lower tail test, we make the critical value negative. Because the z-stat is greater than the z critical value, the data are suggesting that the null hypothesis is true. Suppose for the moment that the opposite was the case, that the z-stat was less than the critical value. Then we'd have evidence in support of the alternative, and we'd reject the null hypothesis at the 10% level of significance. When we reject the null hypothesis at 10% level of significance, we state the alternative hypothesis affirmatively. So if the null is rejected, then we accept the alternative, which means less than 70% of economists believe the stock market will go higher. However, because the z-stat was larger than the critical value, we cannot reject the null hypothesis at the 10% level of significance. Because we cannot reject the null, we cannot conclude that the alternative holds. I.e., we cannot say that less than 70% of economists believe the stock market will go higher. And that concludes case 8 of chapter 9, the lower tailed proportions test.